All right, I'll hit record. That means we're officially back in business. My voice lasted for the first class, so I'm optimistic that we're going to make it until this one. I've got my Sprite, I've got my water, I've got 4 cough drops and Kleenex. Like, I'm ready to go here. That's all I can do. I decided not to bring my humidifier to campus, so I'm pretty sure introducing extra moisture into the computer lab is not ideal. So we'll make it work. I did post something today that I did not tell you about, so I want to tell you about that now. I know. I made a little spreadsheet. It's posted for today. So this morning I was reflecting on how Tuesday I felt maybe didn't go the best. Let's just, proprioceptively as an instructor, you can tell sometimes when like folks are with you or you feel like you're sort of on, and Tuesday was not a great day. So I was sitting there thinking like, okay, how do I make this better? And I was like, I should do one of those spreadsheet examples where we just like sort of layer in numbers and we go through it slowly. And so then I thought, oh wait, like, did we do that last year? Like out of nowhere, yeah. Now I found the exact spreadsheet that I was building in my brain this morning, and I did it last year. And not only did I do it last year, I did it at this exact day last year in terms of week 4. So apparently I am internally consistent in sucking at presenting this and then trying to think of a way around it to make it better the next time. So I have this for us to go over as a way of reintroducing the topics we were talking about last time and trying to connect it all together, because this is one of those topics that can be a little overwhelming in terms of the sheer volume of things to keep track of. So that's what I wanted to do. And you can either download it and play along, or you can sit there and watch me type, because I'll post the finished version when we're all done. How's that sound? Good? Okay, so this is Excel. There's nothing wrong with Excel. Excel has a lot of uses for doing quick calculations and organizing things, such as little examples like this. My brain works in spreadsheets. That's just how I think. So what I have here is an example trying to illustrate all the pieces that go into making this decision right here as to what we would call a relationship. So the context of this is we're talking about one slope so far in a general linear model, right? So in such a model, we would have a fixed intercept that tells us what our expected outcome is when the predictor the slope is for is 0. So in the example, we had a predicted level of income for somebody with a high school degree, for instance, as our predicted intercept. And then the slope tells us how the predicted outcome changes per unit of the predictor. And so that's what we're talking about here, is all of the pieces of information about that slope and how we would describe it and its expected inconsistency. One of the things you can be working on, by the way, is your next formative assessment that is due Monday. Hillary's going to take that. She's very excited. She's already answered all the questions. And I will tell you that it will be a vocabulary drill of predictors and slopes and intercepts, and it will hopefully get you ready for the homework in which you can apply these things at one more level. So this is kind of like a test run, so to speak. This stuff we'll talk about in the next formative assessment the following week. So I scheduled 2 back-to-back because I knew it would be a lot of concepts in a little bit of a time. So HO, what's that called?
Null hypothesis.
Null hypothesis. What's it mean? In Zoomers, you can talk or you can type. I don't know if we'll be able to hear you, but I can certainly read what you type.
That's when doesn't have to be, but usually it means a difference of 0.
Yeah, it's like what we expect to happen.
Okay.
And in almost every case, it's 0. Yeah, so a slope of 0 means what conceptually?
There's no relationship between the predictor and the outcome.
Exactly, no relationship. If I know what your score is on X, I have no idea what it is on Y. They're unrelated to each other. So 0 represents our expectation that 2 variables are unrelated as a starting point, and then it's like, prove me wrong. Okay, let's go. Slope estimate of 6. What would that mean? If I had to put 6 in a sentence.
That for every unit of predictor, the outcome would change by 6.
That's right. For every unit of the predictor, the outcome would increase or decrease? Increase. Yeah, the sign. So I've got 4 scenarios here. 2 have a positive slope of 6, 2 have a negative slope of 6. So if I had a negative slope, I would say as x goes up by 1, y goes down by 6. Do you think positive 6 or negative 6 indicates a stronger relationship?
Well, it depends on what it is. It'd be the same.
It's the same. Yeah, so the sign reflects the direction of the relationship, but the amount is the same. So I would say these are of equal magnitude. So the sign just tells you which way x goes or y goes. Next one over, slope standard error. Conceptually, what is this telling me? Do I want this to be big or little? Take a vote, big or little? Yeah, little. I want it to be little. Error, right? Error little. That makes sense? What does 2 mean in this context? Make these a little bigger. This one's a little trickier. You will answer about 4 homework questions for this, just so you know. This is a definition that you will see repeatedly. Who's feeling brave, or who has found it in their notes first?
It's like how far off the slope estimate potentially is.
Yeah, how far off? So standard error always starts with that. It is the expected difference between what the slope would be in any one sample on average relative to what it's supposed to be in the population. So the term I use for this is inconsistency across repeated samples of the same kind, or wiggliness. Like if we redid this study, we're not going to get a slope of exactly 6 back. It's going to be some number around there. The question is, are we talking about 5.9 to 6.1? Are we talking about like negative 12 to 18? Like how wiggly are we talking about? And so this is essentially a standard deviation across the sampling distribution of what the slope would be across multiple tries. So at a higher level of abstraction.
Did you say, right, that's correct,
Yeah.
expected difference, I'm not sure what you said, from the sample slope to the population slope?
Yep, that is what I said.
Oh, nice.
Yes. So I can make it even simpler. A standard error is how far off on average the sample whatever is to the population whatever.
Okay, that makes sense.
So mean, intercept, slope, everything has a standard error. Yes.
So for example, as this, does that mean the population slope should be 4 to 8? And just
Yeah.
6 minus 2 and 6 plus 2?
So plus or minus 1 standard error would mean 4 to 8 is what we would expect. Generally, when we build intervals like that, it's plus or minus 2 standard errors, because then that would be about 95% of the slopes across. So yeah, somewhere between 2 and 10 is what we would expect this to be across repeated samples.
Okay.
Yeah, so kind of wiggly in this case. I have a picture that goes with this. Let me remind us what that picture looks like. Yep. So this is slide 29. This is me playing God. I built a data set that had a linear slope relating an x to a y of 2. I did that in like 100,000 cases. Then I drew repeated samples of either 10 people, 30 people, or 50 people. So going across here, you'll notice what happens to these distributions. As we get more people in each sample, what happens if I go from left to right?
Squishes in.
Yeah, smushes in. There's less dispersion. So another way you could think about it is the standard deviation of this distribution is smaller. The average discrepancy of any one slope from the population slope is reduced the more people you get. That's a standard error. So the standard error across potential slopes, like that's standard deviation, is the standard error across potential slopes. I need a drink. I can feel my words like rushing out before I start coughing, which is never helpful. Okay, let me speak more slowly. If you have a collection of samples, we talk about how distributed they are using standard error. If you have a collection of people in a sample, we talk about how distributed they are using standard deviation. Same concept, just a different level of abstraction. So as we go from left to right, as each of the individual samples gets bigger, there's less fluctuation in the slope we get back, less inconsistency. But if we go from top to bottom, the top rows have a standard deviation of the people of 3, the bottom have 5. So we can see then that the distributions are more spread out if they have a higher standard deviation. So the more variable your people are from each other, the more variable the slope they're going to create is going to be across samples. So all things being equal, standard errors are smallest if you have larger samples, and those samples have less variability across their people. Okay, how is that? Thumb checks. Good. Zoomers, how we doing? It's like a sea of names. There's some thumbs. Don't be shy. And at least one of the TAs, Hillary, are you on Zoom? No, you're not. Okay, Michael's on Zoom, by the way. If you want to ask any questions, you can send them his way or you can direct message me as well. Okay, back to my table. I made the math easy. Because, we're not going to do math. So, slope relative to 0. 6 seems like it's pretty far away from 0. How far is it expected to be on average? 2. Okay. So if I take 6, I divide it by 2. We get 3. 3 has a special name. That is my test statistic. It's almost impossible to say. Because we're going to treat the test statistic as a t, using the t distribution, you will hear me say t value. That's a little easier to say. So estimate minus null hypothesis of what it's supposed to be, divided by the standard error for the expected inconsistency, gives me this ratio of 3. That's my test statistic. Okay, now what the hell is that? Is the next question. Or why do I need to know this? Let's think about units here. I can't tell you without any additional information whether 6 is a lot, because slopes are in units. So this could be like per inch, per pound, per degree, per test score, per whatever. Like we don't know what the units are. I can't tell you if 6 is a lot. But what I can tell you is that a slope is the change in y for 1 unit change in x. So the units have to do with the variables in the question. Likewise, to compute a slope's standard error, the ingredients are residual variance for y in the numerator, the variance of the predictor the slope is 4 in the denominator, multiplied by sample size minus the number of fixed effects that you spent. So that is also in units of y per x. So if I take this fraction and divide that fraction, the units cancel. So then this is in units of t, which is standardized. So now I don't need to know what y and x are to tell you that 3 is good. 3 means that I am 3 standard errors away from where I would expect to be if the null hypothesis is true. And that's where we come down here. The boundaries as to what is expected are almost always about 2-ish. So as a general principle, if you are more than 2 standard errors away from the null hypothesis, you can call your result significant. So for a 3, why is my x-axis gone? Well, this used to have labels of 0, 1, 2, 3 on here. I'm out here in the tail, essentially. If I can make that bigger. Oh, there we go. I just squished it somehow. So at 3, I'm out here. How unlikely is it that I would get a result that's 3 standard errors away from what I expect? Well, to know that, to figure that out, I got to know some other things. My denominator degrees of freedom in this example are 8. How many people must my sample have had to end up with 8 degrees of freedom? Close. Formula's right there if that helps. Close to 9. Got to vote for 10.
10.
Anyone else want to vote?
It would be 10.
Yeah, it is 10. So n is 10 minus k is 2, because to fit this line, we had to have an intercept first and a slope. We had to know 2 things. So denominator degrees of freedom is built from sample size minus the number of things you already had to figure out to do this. Things you had to figure out, estimated parameters. Stuff you had to know. There's another one for you. So, yeah.
Intercept is this thing and slope is this thing.
Intercept is this thing,
Okay,
and slope is this thing.
yeah, okay.
In the pictures, let me find that one.
No, intercept is like what we're centered on.
Yeah. So intercept would be like, where would you start on y
Okay.
when x is 0? So you got to start somewhere, and then from that point, where do you go? Yep. So you got to have an intercept first, and that's why in the formula for sample variance, it's n minus 1, because you had to know what the mean is to even do it. In the population variance, you pretend like you know the population mean, so you didn't have to know that first. So that's why it's like n instead of n minus 1. But for us, it's n minus 2, because we would have to know the fixed intercept and the fixed slope in order to be able to do this. Now, is 10 people a lot?
So why would it not, this is irrelevant to what we're doing right now,
Okay.
but why would it not be 3 if you had to estimate the mean in order to get the intercept? Because you've already accounted for that.
The intercept and the mean are essentially the same thing,
Okay.
because the fixed intercept becomes however the mean of y needs to shift given the mean of x. So it's still this kind of idea, it's just that is it the grand mean or is it this mean specifically here as an anchor point for the reference?
Okay.
So the mean is replaced by, so let me back up. Okay. Either way, this is slide 27. I've got this intercept here, I've got this intercept here.
Mm-hmm.
They are the same thing in the sense that they provide a location on the y-axis. They provide a different location though. This is from an empty model, hey, not that, where because there are no predictors, there's nothing to condition this on as a reference, this is just the mean. So if I don't know anything else about a person, my best guess for their outcome is the sample's mean, so that's what this takes on. Now down here, I do know something else, I know their education, so the grand mean converts to the mean specifically at education 12, a conditional mean, or an expected mean instead. So it's like it's taking this thing and customizing it, tailoring, so to speak. Does that help?
Yeah, I think so. Yeah.
Cool. Okay, other things I'm going to try and help with as needed. Don't be shy. All right. Okay, back to this. 8 people or 10 people with 8 degrees of freedom, not a lot, right?
Mm-hmm.
Well, this could be a pilot study, meaning you don't have a lot of money, you're just going to get a little bit of data to see what happens. This could be your life. So if you study special populations where there's just not that many people, then maybe 10 is the best you can do. In Excel, there are functions built in to tell you exactly what your t-distribution should look like given your degrees of freedom. So if you can see, yeah, you can't, I can't blow this up, but you can see it if I click in it here. T.m.2t. So that is going to return the value on the t-distribution. Can you guess what 2t stands for?
Two-tailed.
Two-tailed, yes. Given where unexpected is going to start, so 0.05 means I'm saying 5% is what I'm going to call unexpected. And if it's a two-tailed test, because I'm not cheating, I'm going to put 2.5% over here to allow for the possibility that my slope is greater than 0, and 2.5% over here to allow for the fact that it could be less than 0. Because if I find a negative relationship, I want to know about that. If I find a positive relationship, I want to know about that. What else would I call how much unexpected is? What's a vocabulary word that goes with this? This decision to say 5%. Starts with an A.
Alpha.
Alpha, hooray, we got it. And so after all that, then it's like, what is the degrees of freedom? Because that controls the flatness. So let me find, I got a picture on that too.
39.
There it is. So this is slide 39. Yes, thank you. So I stole this from somewhere. Every semester I go and I check the links to make sure where I stole it is still where I stole it from, and this one's gone. So thank you, whoever made this picture. It's just, I don't know where it came from anymore. But the black line here is what the z distribution would be under the standard normal. So this tells us essentially what our slope distribution would look like across the repeated samples, and like where ours would be if the middle is the null hypothesis. And for degrees of freedom 6, that's the blue line, starting to get a little squishier. 3 is the red line, even squishier. So these are distributions that, like, because math, like, people have figured out how this works. We don't have to go through that process and reinvent the wheel. So you can figure out exactly what your shape should be based on your alpha level and your degrees of freedom here, and that returns 2.3. So note, this is the same across all my scenarios because it's only based on sample size. So 2.3 is then where the boundaries would be for the green lines. That's dictating where unexpected starts, where 2.5 is after that, 2.5 is after that. So this is the basis of 2-ish. This is 2.3. Now, what if reviewer 2 comes along and says, I don't like this. I think that you have some alpha inflation going on, maybe some p-hacking, some researcher degrees of freedom with forking paths. Yes, these are all expressions that you will see in the literature now. She's laughing. Am I right? These are all things. I think that you are not being conservative enough. Okay. What if I declare 1% where unexpected starts? Then I really have to have something to be able to say, yes, this is different than what I would expect. Well, plug that in here. Now my goalposts are further out. They're all the way out at 3.3. Excel will also compute exact p-values. So this one, come on, trying to get there. There we go. Is based on t, denominator degrees of freedom, and it's for a two-tailed test. So what this is telling us is the exact probability of observing a slope of 6 at this sample size, given this expected inconsistency, if the null hypothesis of 0 slope is actually true. We would find a slope this big about 1.7% of the time. Is that sufficiently unexpected? Nah. So if I were doing my original boundaries, which you're supposed to set ahead of time, how would I label this result? I have a positive slope. If I'm using an alpha of 0.05, would I call this significant or non-significant? Here is your decision points. So we are at a t of 3. We're out here somewhere. What do you think?
Well,
We're out here somewhere.
so are we saying the 1.7, is that from the end to here?
A 1.7 is the probability after that point on either side, essentially. So if I have an alpha of 0.05, my boundary is 2.3 as to where unexpected starts, but I'm at a 3. So I'm in unexpected territory. Significant. Significantly. And is 6 a positive number or a negative number? Positive, that's it. Yep. As x goes up, y goes up. So under this standard, under this alpha of 0.05 as to where unexpected starts, we would say, yes, this is unexpected. Da-ding! What if we were using reviewer 2's suggestion? Yeah, then we haven't crossed this boundary yet. And in fact, that's what the p-value is telling us. Somewhere between 0.05 and 0.01 is where we are. We're at 0.017. So I would say this is non-significantly positive. That's what I would say. I've had people yell at me about this before. I can't spell positive in front of people. Positive. There we go. Tiv. I swear I have a PhD in everything. There. True null hypothesis, like dyed-in-the-wool people would say anything that's within expected territory is 0. You don't get to talk about direction. I don't believe that because I think that people who want to know how your study turned out they'd want to know that it was positive and not significant as an extra piece of information that you could tell them. I think direction matters. Okay, how are we doing? Do you want to do another one? Okay, same slope as 6. But now we're from a sample that has more inconsistency, standard error is 3. How far off from the null we are, divided by average inconsistency, gives me my unitless t ratio of 2. Well, I'm only at 2. By either standard, it's within expected territory. And the p-value is greater than either 0.05 or 0.01, depending on how you set it up. So in this case, I'd call this non-significantly positive as well. The next two, I don't think we have to do. Do you see the trend here? It's in the opposite direction. T is negative. That is how it's supposed to be because it carries the sign of the slope, which means we're over here on this half of the distribution, but it's the same deal. Same set of conclusions, same logic. So this one, if we were using an alpha of 0.05, significantly negative. And this one would be non-significantly negative. Now you will hear all kinds of euphemisms for p-values that are not significant but are close, like 0.08, trending, marginally significant. My personal favorite is approaching significance, because that one makes it sound like a cake. It's like just not done yet, but if you come back later, it'll be significant, like it's approaching, like as a dynamic process. It's like, no. But this also illustrates why you're supposed to pick your alpha ahead of time. I want 0.01 because I want to be strict. Here's my result. Did I say 0.01? I meant 0.02, actually, because I want to call this significant. So this is where you get into sort of potential for shenanigans, let's just say. But you're supposed to pick your lane ahead of time. All right, what if my pilot study was a raging success and some grant agency that isn't dead yet decided to give me a bunch of money? Could that happen? Sure. Let's say that I went out and got 500 people, because I got a bunch of money. What are my new denominator degrees of freedom if I have 500 people and I fit the same model? 498. 498, that's a lot better. Okay, now watch what happens. Copy that one. Yeah. See, the numbers are changing? These ones, all the same. Our slope is still 3 standard errors away from the null or 2 standard errors away from the null. What more people do is change where the boundaries are. They push them in. So it's easier to get into unexpected territory. So now, the exact same pattern of results at a higher sample size would be significant by either standard here and for sure by 0.05 here. And what if I had 1,500 people. At some point, the boundaries stop. So you hit the edge here of 1.96 is where like infinity is in terms of these things moving in.
And we would be essentially on a Z.
And that's where you're at a Z at that point. Yep. Yep. So then in the limit, as they say, as n goes to infinity, you end up at this black line, and that's where you stay. In practice, what you're going to see on your output, though, is those 3 columns and that column. All this middle logic as to where the boundaries are, that's done for you. So it just returns the exact p-value. What is the probability of getting a result this strong or stronger if the true result matched the null hypothesis, if the slope were really 0? That's what this is. So it's a probability. Okay. I think that's all I wanted to say about that. I will post the finished version of this after class so that you can download that for your future reference if you wish. Any questions or comments or things you want to hear again? Question, comment?
The only thing is on that second row where you have the huge sample size, when you post it, you might want to change the conclusion first, that just so that people aren't confused.
What a great idea. How about I do that right now so that I don't forget? So in this case, we have, this is significantly positive. It would be non-significantly positive here and here. Oh, negative. Copy, paste, copy, paste. Nope. And there. How's that? Check my work.
You do the one, there's one on the bottom that
Okay.
needs to be fixed. The significantly negative.
Yep. This one should be there. That look right? Okay, excellent. Now it's ready to be posted. Thank you for humoring me. One of the best pieces of advice I got is always fix your typos immediately. Always. So after class, if I ever have things to fix, you will see a new version of the slides posted so that my mistakes are fixed. It's always impressive when I find a typo that I've had for years, and I'm like, how did it happen? We were just talking about this. Like, there was one slide that I swear to God is at least 10 years old, and someone found an error on it. I'm like, how have I not seen this for 10 years and no one else did? It's amazing. But it happens. Okay. So then, whereas I have this. Okay, let me start here again. We have a little bit more to do, and then we can look at an example. So I'm on slide 43 of lecture 2 here. So what's in your output? Estimate and standard error are really the only things that you absolutely need to report. Those are going to be the first 2 columns. So estimate is what happened. Standard error is the expected inconsistency of that result across repeated samples relative to what the null hypothesis said it should be. Estimate divided by standard error gives me my t-value, my test, that says, where am I relative to the boundaries? Denominator degrees of freedom, say where the boundaries are. The p-value shows up as a function of where you are relative to what your t-distribution boundaries say. This tells you the probability of observing a result that extreme or more if the null hypothesis is true, where you're on a distribution where 0 is the null and the standard deviation is the standard error. So t tells you how many standard errors away from the null you are. And sometimes you can put that into a confidence interval as well. So here's computation of the standard error for the slope. We went through most of this stuff here. And then there were some questions about that last time as to what's good and what's bad. So 1.82 is the slope in this example for how education predicts income. For every additional year of education, income is predicted to be higher by 1.82. The expected inconsistency of that slope across repeated samples of the same kind is 0.16. So right now, I don't know if either of these numbers is good, right? I'd have to know the units. I don't know what like the maximum slope would be for a perfect relationship. But relative to each other, once I put this into the t ratio, now I have a number that I know what to do with regardless of what my data are about. A t value of 11 means I'm 11 standard errors away from the null. That's pretty unexpected. So I don't need to know what x and y are to know that 11 is far away. And by any standard, it would be declared significant. So in intro stat, there's a whole lot made of reject the null and retain the null. What does reject the null mean in terms of significant or non-significant? Which one is it?
Significant.
Significant. And if you're non-significant would be either retain the null or do not reject. I'm not going to die on a hill about that. I don't care. Yeah. People don't talk like that. They don't. So this is all these numbers here. Like this is the sentence that I would write. Predicted income is significantly higher by $1.82 thousand for each additional year of education. That's what I would say. So then in parentheses, reject the null that the slope is actually 0. So we can build standard errors and confidence intervals for other things, like predicted outcomes. Let's say that you wanted to use the results of this study to forecast what predicted incomes would be in a new sample. Well, you'd also want to know how wrong your forecast is likely to be. Like how much error is there around the regression line? So here's an example of building a standard error for y hat. There's a vocabulary word. What's y hat? This thing. It's what?
Predicted.
Predicted y. Predicted from what? Say again?
Sample mean.
Sample mean could be one thing. In this case, we've got a custom mean that is conditional on education. But we have education predicting the outcome as well, right? So y hat is an abbreviation for the predicted y from the model fixed effects. So the part that has to do with the estimated constants, beta 0 and beta 1, and the predictor that multiplies beta 1, but not e. So y hat is everything but e. That means anybody who has an education of 12 would have the exact same predicted y hat. Anybody who has an education of 10 has the same y hat. So it's still a mean in the sense of being like an aggregate for a certain kind of predictor value, but then E would further differentiate the individual in question. So E is how wrong the model still is. It's a residual. So if I wanted, go ahead.
So
Yeah.
y hat is like, if we were talking about someone with, 14 years of education, then y hat would be the predicted average for people within that
Yep.
column.
Then y hat
Okay.
would be for anybody who has a 14.
Okay.
Yep. And as we add more predictors, it gets more precise, right? You're a 14 on this, and a 5 on this, and a 2 on this, right? So your y hat looks like that for that profile of scores. Yeah, it's an abbreviation, but you'll see it in the notation a lot, which is why I want to make sure that we're good with that. So in this case, I'm using this formula to describe a standard error for a predicted outcome for the intercept, for this 14. So what is the expected inconsistency in predicted income for somebody who has a high school degree? Well, according to the model, we would put in, we have residual variance of the outcome. We have how far away the predictor is from its mean. Did I bring my thing? Hang on. I think I brought my prop. Did I bring it? No, I think I left it at home. I left my stick at home. I'll just have to do my arm stick then. So if I have a slope, the values at the end of my arms move a lot more if I tilt my slope than the values in the middle. So the things in the middle are going to have the most precision because there's the most sort of emphasis or weight at that point to be able to capture what they should be. The further out you go, the more it's uncertain. So that's what this is capturing right here. So I can use the standard error for that point and build a confidence interval. So 14 is, on average, what I would expect for somebody who has a high school degree. This is the interval that describes the imprecision around that prediction. Here is a picture that shows that for the data set this example came from. So do you see the blue line here that has like a blue shady line around it? The shady line is an interval built on standard error. So it gets wider as you go out because there's more uncertainty in what those predictions would be based on the slope. And you see the dotted lines out here? That's the prediction if you take into account the error variance of all the reasons why you're wrong. So it's a lot wider because there's a lot of unexplained variance in this model. So if you were to develop predictions, you would want to have standard errors that go with those predictions. Standard errors are not often provided in real life, which is interesting. So most of you had to take, or not most of you, some of you had to take the GRE to get here, right? Not all programs require it anymore. I had to. Hillary, did you have to?
I did, but you don't have to.
You don't have to?
anymore.
So you know what's interesting about GRE scores? They give you the scores. They don't give you the standard errors to go with them. So you don't actually know how wiggly your score would be if you retook the test, which is what it's supposed to tell you. So when people make differences, oh, this person got a 155 and this person got a 156, that means they're more qualified. What's the standard error of measurement around that? Are you going to tell me 155 and 156 are meaningfully different? Probably not. It used to be the case that ETS, who publishes the test, had this guide to interpreting test scores where they actually had standard error information, and they were huge. Huge. So when I took the GRE, it was on a scale of 200 to 800, and like the average math score was like 550, and that was the point where people sort of, that was like, maybe you get into grad school, maybe you don't or something. Do you know what the standard error was around 550 at that time? 50. So if I go 2 standard errors around that, somewhere between 450 and 650 is what my math would be if I got a 550. That's like all the range of variability of my applicant pool. So yeah, it's woefully unhelpful if you want to have something that's precise. And that is why I do not even look at those scores. Because until you give me a standard error for what it actually means, I'm not going to pay attention. So when you're faced with real-world testing data, right, you get some kind of score back for your kids or for an exam, like for licensure or something, find the standard error. See if it's there. Yes?
I tried to find out once.
Oh, yeah?
She didn't know.
She didn't know.
And kind of like blinked back at me like, what?
Yep.
But
It's usually
okay.
buried. Like if you look up the testing manuals or the documentations that go with things, it's buried. But it's often given in terms of a reliability coefficient from which you can work backward and figure out what standard errors would be.
Well, it kind of negates the reason for testing. If
Yes, it does.
if as long as you're on the scale somewhere, you fit.
Well, if you think about high stakes decisions, so like I'll give you an example. My dad about 20 years ago had to take some kind of physical ability test for a position, and he had to do a grip strength as part of that. He didn't know how to use the grip strength thing. He didn't understand the instructions, and so it said that he had terrible grip strength, and he came home really upset, and he's like, I could throw a 16-pound bowling ball. So I got grip strength. Like he couldn't, this was invalid or whatever. So we get to the point where like his score was like 1/10 of a point too low to meet the standard for whatever this job required. And it's like, number one, he needs to redo the test so he can actually understand the instructions. But number two, are you going to tell me you have a standard error that's less than 0.1? That's going to tell me that he is meaningfully less fit than whatever this cutoff is? No. So I'm kind of on a tangent here, I'm sorry, but imprecision around the score is something that you have to always consider, not just the score. That's why when you have poll results that this candidate is up by 5% or this candidate's up by 2%, there's always margin of error at the bottom of the screen. Oh, they're up by 2, but the error is 10. Are they up by 2? No, they're not. It's all error. So we need that. Okay, new topic, sort of. 1.82. This slide tells me what about it? P less than 0.0001. What's the label I would affix to that, given that?
Significant.
Significant, meaning significantly unexpected if the slope were actually 0. It would happen very infrequently that I would get a slope this big if it were really 0. Cool. But I know that if I have enough people, eventually everything's going to be significant. So is it a strong relationship? Is it a weak relationship? Significant doesn't tell me that. Significant is strength plus precision based on your sample size. So if I want to know in a more absolute sense how strong this relationship is, one way to think about it is to take that slope and strip away the units so that it is standardized. So for example, here is a handy-dandy conversion formula by which you can compute a standardized slope from the unstandardized slope that is in units of x per units of y. You essentially invert it. So if you take your slope and multiply by the standard deviation of x divided by the standard deviation of y, you get the standardized version. So if I do that for this data set, given these descriptive statistics for x predictor and y outcome, I get a standardized slope of 0.38. Standardized means it's supposed to be on a range between -1 and 1, where 0 means 0 slope. This one's 0.38. In models in which there is only one slope, this has a special connection. It is equivalent to what is known as a Pearson correlation, R. Does that ring any bells? Hopefully. We've seen R before? Yeah, Pearson's a dude, and correlation starts with a C, but we're going to call it an R, all right, just because. So this is a measure of bivariate association, meaning two variables at a time, where it is computed by stripping off the units, essentially. It is a slope if the two versions of the variables had been converted into z-scores, as shown here. So x minus the mean of x divided by the standard deviation of x puts x into a scale where 0 is the mean and 1 is the standard deviation. Do the same thing in y. Then the relationship of how y and x are related, for every 1 unit change in x, y goes up by 0.38 in standardized units. So this is going to be what is known more generally as an effect size. An effect size is changing a slope into a metric to where people are like, oh yeah, I know what that means. Like it has an absolute meaning beyond just the units in question. So if you don't remember Pearson correlation, here's a brief refresher. This is slide 48. And I did find a person who I stole this picture from, so there's the link if you'd like to know where I took that. So these are scatter plots. I have x on the x-axis, y on the y-axis. If two variables have nothing to do with each other, a plot of their x and y values would look something like this. If x and y are perfectly positively related, it would form a line like this. Lockstep, if I know what x is, I can predict your y. Not perfect, but still strong would look like this, and weak looks like this. And then if we go the other way, negative slopes form the same pattern. So a correlation of 0 is neutral. It corresponds to a slope of 0. Correlation of 1 is as strong of a relationship as you can have in the positive direction. Correlation of -1 is as strong as you can have in the negative direction. Is one stronger than -1? Nope. It's just a question of which way they go. So this is an effect size. If I only want to know how two variables relate to each other, this is what I can do. And I will end up with the exact same information as from my one-slope general linear model. The p-value for my 1.82 slope in unstandardized units will exactly match the p-value for my standardized slope of 0.38 in non-units. It works out to be the exact same thing. By the way, Pearson's correlation has a few synonyms under certain cases. So if you have two binary variables and you're correlating them with this formula, it is called either phi or phi. Take your pick. Can we get a vote? Anyone care? Phi. You're going with phi? Phi, phi, pho, fum. I don't know which one. Phi, phi. Take your pick. Also, if you have a Pearson correlation between binary and quantitative, that is called point biserial. So these terms show up in testing contexts a lot, but they're still just Pearson correlations. There's nothing different about the machinery by which these are being estimated. Okay. Now you might be asking yourself, so you took 47 slides to reintroduce correlation to me? Is anyone asking themselves this question? Like if that's where we're at? There are many good reasons why models will be more flexible and useful to you than just Pearson correlation. One is if we look at the pictures here, what kind of relationship is being captured here? What form of a relationship between two variables? Starts with an L is the word I'm thinking of. Linear. Yeah, linear. So we fit a regression model where we drew a straight line, and a Pearson correlation is essentially trying to capture the same slope of that straight line in z-scored variables. But is it possible that more x is related to more y up to a point, and then it kind of doesn't matter? Like, are money and happiness related? Well, if you can't afford to eat, you're probably unhappy. But at some point, if your needs are met, then maybe there's less of a relationship. Another example of a nonlinear relationship would be a performance arousal curve. That's a fairly classic one. If you have an important thing to do and you don't give a shit, or you're really, really freaked out about it, you're not going to do as well as if you're somewhere in the middle in terms of like you're invested but you're not like over the top. So those kinds of nonlinear relationships would not be picked up with this technique, but they can be picked up if you put them into the model with additional slopes. Also, if you want to know what happens for more than one variable at a time or two variables at a time, this type of thing starts to not be as useful. So models can do a lot more stuff, but at its core, we've just recreated a Pearson correlation. That's what we've done. Start with. So this is an example with a quantitative predictor. What about categorical predictors? Do you think we can use those? Sure. So let's start with the most simplest kind, relatively speaking, binary. So in general, if you have a predictor variable that's a grouping variable, so kinds, if you have C different categories, your model needs to have C fixed effects to fully differentiate all the categories in their means. That means that one of those fixed effects is going to be considered beta 0 for the intercept, so we just need C minus 1 others. So if I have a binary variable, I need one slope. I just have to get from the 0 value up to the 1 value. So that's one line that can possibly connect those 2 points. So for example, let's say that x is binary, so that 0 is the reference category and 1 is some alternative category. This same model would then get a new name. I'm going to call it general linear model. Other folks would call this an independent t-test or a two-sample t-test. Those sound familiar? Maybe? You're comparing two means, right? Well, that's what I'm doing. By putting in a beta 1 slope, I'm allowing the mean for 0 to differ from the mean for 1 for this x variable. So in my example, I have a variable for marital status, and 0 means someone is not married, and 1 means they are married in this example. The intercept has the same definition, and the slope has the same definition. We just have to think about how we talk about it a little differently. So what's an intercept? Back to vocabulary. I'll accept gestures or words. What's an intercept? Zoomers can play too.
The one that's like on the y-axis.
The one that's, yep. So if I were to put a verbal label on it, can you define intercept for me? Because you're right.
Like in terms of a model,
Mhm.
if x is 0, it's the outcome.
Yep. The intercept is the expected y value when x is 0. Yep. Where we are right here if x is 0. So that is still true if my x is a category and not a quantitative variable. So given the coding scheme here, my intercept is the expected value of y when x is 0. That is for unmarried people. So rather than for 0 years of education or 12 years of education, it's unmarried people is what 0 means. A slope is still the change in y for a 1 unit change in X, but a 1 unit change now refers to going from being an unmarried person to a married person. Same machinery. So beta 1 now is going to say what the expected mean difference is for married people relative to unmarried. And you will hear me say this repeatedly this semester and for a reason. This is very easy to screw up. The slope for a binary variable always tells you how the 1 group differs from the 0 group. So if the slope is positive, whoever's coded 1 is higher. If the slope is negative, whoever's coded 1 is lower. And it has to be said that way, otherwise the direction gets flipped. So E then is still the discrepancy between what the model says income should be and what it actually is. So E is still how wrong the model is for this particular individual. And this slide, for whatever reason, hang on, stop, back, there we go, always has 2 of the lines shoved over for no reason. It has been like this for like 7 years, and I have yet to figure out why it does this. But every single time, I have to manually move these 2 back. I know that it's coming. So here's a fit plot from SAS, actually. For x-axis is married. 0 or 1 are the only choices. So that's why we have a stack of dots here and a stack of dots here. It's still a scatter plot. So here's the solution. The slope works out to be 6.22 with a standard error of almost 1. T-value of 6. Is 6 good? Yeah, that means that if the true slope were 0, I'm 6 standard errors away from it, well into unexpected territory. Would happen very, very infrequently given the p-value here. So if I want to build a prediction then, for somebody who is unmarried, I would still use the fixed intercept of 14.545 plus the slope times 0, because that's what it is for unmarried people, leaving just the intercept. My residual would be what it actually is minus that prediction. For married people, the difference is that I plug in a 1, and I get a different prediction here. So then I would say that married people, the 1 group, are predicted to have significantly higher income, higher because the slope is positive, significant because it's 6 standard errors away, so the boundaries are about 2, so 6 is further out than 2. So it's a roundabout sort of way, but this is a 2-sample t-test. Literally this t-value, that's what you would get if you ran it as a t-test in your software. The advantage of doing it within a model is that it readily expands to other kinds of predictors. What if I had a group for single, married, divorced? Could I do that? I could. Now I'm going to have to change the model a little bit because I couldn't just put in like 0, 1, 2 for single, married, divorced because it's a nominal variable. What's going to end up happening is that I'm going to add a second slope. I would have 1 slope that differentiates between 1 group and another, and then a second slope that differentiates the 3rd group. That's where we're headed. So that's one example of why you would want to do this in a model. Nonlinear effects and interaction terms would be another. But there we are. For binary variables, you can compute a Pearson correlation as an effect size, but it is much more common to compute something called a standardized mean difference. The most basic kind is Cohen's d. Cohen did a lot of things. You'll see his name a lot. Have you seen this before? Standardized mean differences, maybe? Another letter to add to our collection. By the end of the semester, every single letter is going to stand for something, sometimes more than one thing. So this is traditionally computed using the raw data of the difference between the group means divided by their standard deviation pooled together, meaning averaged across the 2 groups, where you can compute it like this. In our case, what we're going to do is use the model results to compute a Cohen's d effect size. So we're going to use this residual variance as the proxy for the pooled variance, so standard deviation in the case of the square root for it. You can also compute use t's to compute d's and r's out of your results. So if you have any kind of slope test, you can convert it into an effect size, and I will help you write code by which to do that. All right, that is a new topic, so I'm stopping there. Okay, how are we doing? 2 thumbs, really? Yeah. We get the that look on our faces. This is why I teach twice a week, by the way. Can you imagine keeping going for another 2 hours after this? You're like, nope, I'm full. Thank you. I'd like to go now.
I
So,
also can't imagine trying to remember the material like a week later, you know, like that would be so hard.
yeah, it's 5 days later. It almost feels like it's, a long time.
Yeah, hearing stuff repeated over and over again is very helpful.
Yes, yeah. That is what we will keep doing, is repeating things. So let me foreshadow what we're going to do next week, because we're not going to do it today, okay? So example 2 then is a curated set of syntax and output across Stata and R with lots of notes and things in it. So rather than running things and showing you that in a video, we're going to walk through this code. I can explain how it works, and we can walk through the output that you would expect and where to find the pieces of information that you need. So for instance, I have a tendency to bold things, like, hey, look here, so that you can find things a little more readily. But if you want to play along in terms of running things yourself, that is where inside the download folder that goes with each of these examples, so hang on, let me get the internet, here we go, for instance, lecture 2 and example 2. So example 2 files right here. That's a zip folder, the same as I had for example 1. The original syntax and output are here, along with the data set. So you can run things, and you can see, like in R, all the output that I didn't paste in there because it's not immediately relevant. So I tend to pick out the things that are most important. But like, here's the full R output for everything that this code would have generated. So it's easier, I find, when we're going over code and output to do it in this way, because that way you're not getting lost in running things and like not generating the right results that we're all looking at. I found that to go very badly. So this is what we're going to do. The other thing I wanted to alert you to is if you're like, oh my God, this is so much. What did she say? I forgot to write that down. Everything that I'm going to say is written down. If you go to the very end of each of my examples, they're very long. This one's only 11 pages. That's actually not very much for me. You will see something called an example results section. And so this is what it would look like if I were reporting this analysis for publication. These are the words I would use. These will be much more verbal, like wordy, than what I would typically do for real, but for pedagogical purposes, I've spelled everything out. So all of the interpretations and things that we'll go over, like this is the prose that would go with it. And this is where you would look for, when you're doing homework, like how to complete the paragraphs, because they're all very standardized in terms of how things are reported. All right, does that help? Make it feel a little better? Okay, so repetition, resources that you don't have to write everything down, and we'll just keep plugging away. Sounds good. How about you get 8 minutes of your life back? Are you good with that? All right, well then thank you for being here. I'll hang out for a bit if anyone wants to chat. Work on formative assessment number 2, yes?
Just as a reminder, I will not be in my office hours on Tuesday if you usually would be coming or wanting to do that. Plan on
Yes, yeah, no Michael office hours on Tuesday, but next week otherwise
that.
everything should be
But
as scheduled. Yep. All right, that's it for now then. Thank you. Have good weekends. Let us know if you need anything.